If you haven't done this homework yet, that's fine. 4.4, it was 9 to 33 every other odd. And then I said 37 to 40 all. 37 to 40 all. Open up your books, everybody, and get those out. And then I said 105 to 108. 105 to 108 all. How'd you do those? So if you haven't done this yet, open up those books, get those questions out, and let me know if there was a particular one that had a problem. 37 to 40, 105 to 108, yes. Right, the error ones. Checking to see what they did wrong. So any questions about any of the integrals, how to do any of those in that first section, 9 to 33? So remember the fundamental theorem of calculus, FTC, said that the integral from a to b of f of x dx was the antiderivative plugged in at b minus the antiderivative plugged in at a, f of b minus f of a. This was our fundamental theorem of calculus. We use this to find the area under the curve. This is the accumulated change. Accumulated change, aka the area under the curve, aka area under the curve. How much is on the graph from a to b? And you find the antiderivative, and you plug them in, and it gets you the area, tells you the area. Is there any problems with any of the equations? Maybe number 17, perhaps? Or 25, maybe? The absolute value problem. Or 33 secant squared. No one has any problems? Maybe I can do some of the 105 ones. 105, 105, 106. Any questions? If no one has questions, I can move on. I'm happy to do the notes on the second fundamental theorem of calculus. We can do that straight into that. Would you like me to go over the... Let me take a poll in the chat. Would you like me to go over the homework questions? Or should we move on? Perry has 17. Finds that to be useful. Sure, we can do that one. All right, let's look at 17. Let's try to do at least a couple of these. Michael Johnson. Let me do 17 and then 105, and we'll move on from there. So again, this is just finding integrals. 17 is a little tricky because it's got the square root. So let's do 17 and then we'll figure it out. 1 to 4 of u minus 2 over square root u du. So with integration, it doesn't really matter the variable. They use x's, they use u's. You're just doing an integral. Du means that we're taking, like these numbers here, the 1 and the 4, are represented by the variable in the u, right? These variables here, this is all u, plugging in the u of 1, u to 4 of this equation here. Now it's very challenging to do this by itself right here as a whole, like all at once. So we can make this equation easier by splitting this up. This is what we do occasionally. We have u over root u minus 2 over root u du. Right, when we split it up like this, right, remember we have an equation on the top here. We can split this into two pieces. This becomes much easier because the u on the bottom here is u to the 1/2. And if I have a 1 minus a half, right, if I reduce these, this becomes square root of 1 over, no, I'm sorry, becomes square root of u minus 2 over root u du, right? When I have the radicals here, it becomes u to the 1 minus half, which is u to the half. So we can split this up and just sort of reduce our variables. Remember how when we divide variables that have the same base, the exponents subtract. Division is subtraction with exponents. So 1 minus a half makes this a half. And then we just do the integral here. So this is going to be, let's see, u to the 1 half, u to the 1 half, and let's make this a little easier. Let's do it this way. Let me simplify this. Integral of u to the 1 half minus 2u to the negative half du. And then I do my little process of powers, right? I add the 1 here. This becomes u to the 3 halves over 3 halves minus 2, and then I have a adding 1 half, adding a 1 here, becomes u to the positive half over 1 half. Evaluated from, I should say 1 to 4 here. 1 to 4 here. So sometimes you will see this little bar here saying this means that this is evaluated, this whole equation here is being evaluated, this equation is being evaluated from 1 to 4. So this is your A, this is your B. So you're plugging A and plugging B. And so, again, we can simplify. We do our little flippy-do here, little flippy-do here. We have 2u to the 3 halves over 3 minus 4u to the 1 half from 1 to 4. So when we plug this in, we plug in the 4 first. We have 2 times 4 to the 3 halves. Make that a better 4. Hold on here. Hold on here. Two times 4 to the 3 halves over 3 minus 4 times 4 to the 1 half minus, so I plug in the 4. It's this thing evaluated from 1 to 4. And then I minus the plugging in the 1. 2 times 1 to the 3 halves over 3 minus 4 times 1 to the 1 half. And break out the calculator, try to figure this out. 4 to the 3 halves power. 4 to the 3 halves power. How do we do 4 to the 3 halves power? Well, 4 to the 3 halves power is the square root of 4 cubed. Well, that's just 2 cubed, and that's just 8. When you see a complicated radical, a complicated fraction exponent, just think of it like a radical. The bottom number is a square root. Do that part first if you can. Do that part first. Square root the number. Can 4 be square rooted? Yeah, it's a 2. The top part is an exponent, like a regular exponent. So that 2 that you square rooted becomes cubed, becomes 8. 2 times 8, that's going to be 16 over 3. Minus, let's see, 1 half of 4, or 4 to the 1 half is 2. 2 times 4 is 8. So that's that first part. Minus 1 to the 2/3 is 1 times 2, that's 2/3 minus 4. And okay, you can get out a calculator now, figure out what this is. 16 over 3 minus 8 is in one parenthesis. And then minus 2/3 minus 4. This whole thing, oh, that's nice, works out to be 1/3. No, sorry, 2/3, 2/3, 2/3. That'll be our answer for this equation. Right, so little tricks with finding integrals, tricks by finding integration, and then plugging in, evaluating, all this calculation stuff. Again, you could probably go here and just plug this directly into a calculator, just the way this is here. It would take a little bit more parentheses and exponents and a little more complicated pieces. But really, that is satisfactory. Once you have all the numbers plugged in, you can go straight to a calculator. Just get your answer there. All right, so that was number 17. Doing an integral, complicated looking equation, we can simplify the equation by splitting it up, dealing with the radicals, dealing with the fraction exponents, figuring out how to make things all simplified. There's going to be quite a lot of that on the AP test, a lot of simplifying, giving you something that looks complicated, but when you dive into it is actually very simple. Actually very simple. So let's look at 105 and 106 just to figure out our points. So they say this is negative x to the, oh, this is negative 2, negative x to the negative first power, evaluated from negative 1 to 1, and they said that this was equal to negative 1 minus 1, which is negative 2. And this is an incorrect answer. Someone tell me, looking at this, where's the problem in here? What is the actual answer? What did they do wrong? Let's look at it step by step. So first question, did they do the integral correctly? Is this the actual integral of x to the negative second power? Is this correct? Take a moment. Take a look at this. Is this correct? Alright, so it says no. Remember how we do the integral? What do we do to the exponent? We do the integral, bring an x back inside. So we're going to add 1 to this. Is negative 2 plus 1 negative 1? Yeah. That seems fine. And then when we have an exponent in our integral, we have to divide by that number. Well, if we divide by negative 1, that's going to make this whole equation just, well, we can just put the negative there instead. So, yeah, this part's fine. That is the correct integral. It doesn't have the plus c, but that's because we're evaluating it from 1 to negative 1. So that part's fine. Now, did they plug it in correctly? Did they plug it in correctly? Is this, well, clearly this part's got to be right. Maybe they just, I mean, clearly negative 1 minus 1 is negative 2, but the plugging in part here, something is wrong. So if we plug it in for them, if we did our own process, we would have negative, right, we plug in the a part, or the b part first, that's b and that's a, f of b minus f of a, so negative 1 to the negative 1, minus negative 1 to the negative 1. Whoa, it's a lot of minus signs. This is the first piece right here. Minus, excuse me, this is the second piece right here. Right, we have these pieces here. Second piece right here. We're subtracting, right, f of b minus f of a. You see this minus sign here. This minus sign is this minus sign here. It comes into the equation. The negative 1 is the negative 1 from the a to the power of negative 1. Let's see. 1 to any power is 1, so this is negative 1. Minus this part here is where the problem was. They forgot that this should be negative 1. Negative 1 to the negative first power is still negative 1 times the negative here Oh, or is that correct? If here becomes negative, it becomes positive, that becomes negative. What am I doing wrong? Negative minus negative, negative 1 to the negative first power. Negative, negative, positive, minus. It seems like it should be correct, right? What's wrong? Maybe I'm the one that's wrong. Negative first power is 1 over negative 1. That's fine. B minus f of a. Who sees the problem here? Minus negative 1. How do you mean, Paradiso? I should have a negative here. Do you want to mute and explain? Yes, but where does this negative come from is my question. We have this, right? Yeah, I think I got the same confusion that you did. It seems like we have... The answer should be negative 2. It seems like this is correct, but there's a problem somewhere in here. I did the derivative here. Add 1 and make it negative 1. Divide by negative 1 makes this negative. That seems fine. And then you plug in, you evaluate at 1. Negative 1 to the negative first power is negative 1. And then minus negative 1 to the negative first power is negative 1, and that becomes positive, it becomes minus. Seems like this is correct. Oh, I think I understand. So the numbers are correct. Numbers are all correct. Why is this a problem? Let's take a look. If you can't figure out the problem in the equation, let's take a look at the graph. What's the graph of this look like? This equation is f of x equals 1 over x squared. And that equation looks like this. Oopsies. Like this. This. Well, you get the idea. It has a vertical asymptote. Asymptote. So the graph is not continuous on the function from negative 1 to positive 1. This graph is not continuous. And so if it's not continuous, continuous, so we cannot do an integral. It means you cannot integrate the problem on the interval. Because you're integrating, you're finding area, well, you're finding area of infinity. not really gonna work. So the graph is not continuous. The math all works out correctly. Like, this is all correct. Where's the problem then? The problem is that the graph is not continuous on the interval from -1 to 1. So it is not possible. Not possible because it is not continuous. Very interesting. Very interesting. Excuse me. So, things to look out for in your equations. Right, things to look out for in your equations. And the same answer is number 106. Again, the same thing. We have passing through the 0 of 2 over x cubed, also not continuous. Thank you, Bianca. Thank you, Bryce. 106, same thing. The integral from -2 to 1 of 2 over x cubed is not possible because 2 over x cubed is not continuous on -2 to 1. There is an asymptote, a vertical asymptote, at x equals 0. Oh my goodness gracious. Continuous. Not possible because the graph is not continuous on the interval. So different things to look out for. You cannot do an integral of a graph that has, well, a discontinuity. Even if it was a piecewise function, well, you have to break it up into 2, and it's all complicated. But if there's an infinite discontinuity, you cannot do a integral along that piece, right? So you have to be aware. Remember when we talked about continuity, all these rules about if it's for the various value theorems, but the intermediate value theorem has to be continuous. To use any of these theorems, the graph has to be differentiable and continuous along an interval for any of these things to work. The integrals, the same rule applies. To do an antiderivative, you have to be, well, differentiable on the interval. And if you're not differentiable, then you can't find a value of the area. All right, a couple interesting things to note there. Letting you know about these problems of integration. So if you haven't turned this in yet, please get that to me. I want to move on to our second fundamental theorem of calculus today. Show you what we're going to do, speaking of continuity, how we're going to address this.